On 31st March 2026, Bosnia had beaten Italy in the penalty shootouts to qualify to the World Cup. One of the key factors that made them win was that they were first to shoot in the penalties. But wait a minute, how could that be true? Both teams have equal chances to win on the penalties, right? Well, it seems like, but numbers say something else. 60% of teams which take penalties first ended up winning it. Nevertheless, in the game, there was 23 men on the pitch, the players from both sides alongside the referee. Despite being just 23, there was two players sharing the same birthday, Moises Keane and Tarek Muharimovic, with both born on 28th February. Is this an accident? To find out, let's explore the beautiful world of probabilities. In probability, we start by defining our universe. We call it the trial space, or omega. It's the collection of every single thing that could happen. If you flip a coin, the universe is just 2 points, heads or tails. If you roll a dice, the universe is 6 points. If you are measuring the life of a light bulb, the universe is a continuous line stretching toward infinity. But before we can calculate chances, we need a way to organize this space. One way to organize this is by using set algebra. An event is a subset of our space. We can perform operations between events, but first we need to define what kind of operations we will use. The union is the logical OR, which means happening on either A or B. The intersection is the logical AND, which means happening on A and on B. The complement is the logical NOT, which means anything that is not on A. The symmetric difference is the logical XOR, which means happening on either ones but not in the other. And there is inclusion, which means if A happened, B must happen too. When we perform all these operations, we build a new set called Algebra of Events. It's a collection that follows these three rules. The entire universe, omega, must be in the set. If an event is in, its complements must be in too. If two events are in, their union must be in too. When we deal with an infinite number of events, we upgrade this to a sigma algebra. This ensures that no matter how many events we have, the result still lives within our system. This is the structure that we will perform our calculations on. Another way to organize this universe is by dividing it into partitions. Partitions are 2 by 2 incompatible sets. Their union perfectly reconstructs omega. This complete system of events allows us to look at the universe one manageable slice at a time. To assign numbers to these events, we must first master the art of counting. In probability, counting is the process of navigating constraints. If a manufacturer produces kits for football teams and can choose any of 10 colors for the shirt, the shorts, and the socks, with the repetitions allowed, we have n to the power of p possibilities. With 10 choices for 3 items, we have 10 to the power of 3 or 1000 unique kit combinations. Okay, we have chosen a kit. Now we move to the tournament, to the World Cup. With 48 teams qualified, how many distinct matchups can we have? So we have 2 slots. For the first slot, we have 48 options. For the second slot, only 47 remains since a team cannot face itself. This is an arrangement. We count every possible pairing where the order who is home and who is away carries weight. The math becomes more nuanced when we look at the tactical board. Suppose a manager has 7 talented attackers in his squad, but his formation only has room for 4 forward players. To find how many ways we can choose his attacking line, we use a combination, or 7 choose 4. In this scenario, we don't care who has been picked first or second, we only care about the final group of 4 players standing on the pitch. Finally, suppose the game goes to shootouts. The manager has his 4 trusty players ready to shoot first, but he doesn't know in which order to send them to the spot. Even with the players already chosen, he has 4 factorial ways of ordering them. Thus, there are 24 different scripts for the same 4 men. With our sigma algebra as the foundation and counting as our tool, we can finally build the probability function, P. It's a rule that maps our sets to a real number. To be valid, it only needs to satisfy three axioms. 1. The probability must be non-negative. 2. The probability of a certain event, the whole universe, is exactly 1. 3. For any incompatible events, the probability of their union is simply the sum of their individual probabilities. This additivity is the bridge between the geometry of sets and the calculus of chances. We define the formula of this function as P equals the cardinal of A over n, with n is the total number of all possible outcomes of omega. But probability isn't static. It changes when we scale it upon different conditions. This is conditional probability. This is to say, what is the probability of an event given that another event happened? The formula of this is the probability of the intersection of the two events divided by the probability of the happening event. It tells us how much information or certainty one event can give you regarding the other one. However, sometimes a piece of information tells you nothing new. If a probability of A stays the same after B happens, we say that they are independent. Their paths doesn't cross. The occurrence of one has no pull over the other. In this clean system, the probability of both happening simultaneously is just the product of their individual chances. And this is an example of two independent events. So I have a coin here, and I have a dice here, handmade. I'm gonna flip the coin and roll the dice. Wherever the output of the dice is, it will not change the output of the coin here. That's why these two events are independent. Another way to visualize these concepts is by looking at the probability tree. Conditional probability is the probability of an event on one branch. Meanwhile, independent events are events popping from the same node. We have built the rules, learned to count, and defined our measures. Now, let's see why this structure is so powerful. Imagine you have a complex event B, a messy, irregular shape that is difficult to calculate directly. But because we have our partition, we can see that B is actually a mosaic. It's made of small fragments, each living in a different slice of our universe. The law of total probability says that to find the total weight of B, we simply sum up these fragments. For each slice, we ask, how likely is B to happen here, and multiply it by the size of that slice. It's a divide and conquer strategy that lets us reconstruct the whole form of its part. But what if we want to reverse the script? This is where we find the bias theorem. Suppose the experiment is over. We know the outcome was B. The effect has occurred. Now we want to look back and ask, what is the probability that it was caused by a specific slice, AI? In this moment, our universe shrinks. Everything besides of B is now irrelevant. The probability we're looking for is just the ratio of the one specific fragment to the total area of the B blob. It's a deceptively simple ratio, but is the foundation of all modern inference. It takes our prior belief about the slices, filters it through the likelihood of the evidence, and gives us an updated, posterior understanding. Before we go, I want to leave you with a puzzle that seems evident at first, but it needs much caution. It is a test of how well you can update your universe. You are in a game show, where you're faced with three doors. Let's name them A, B, and C. Behind one is a new car, while behind the other two are goats. You choose the door, let's assume it's A. And now the host opened door B, and there was a goat. And then he asks you, do you want to change the door or stick with door A? I'll let you figure out the best option to get the prize.